I'm Case. I'll be doing number 9. So we have this plastic block attached to a vertical plate here, and the plate has like a load on it, and it's asking, oh, the deflection of the plate, yes. So we have our delta equation, and I'm going to use the flag equation, I like to call it. So I have my force.
Ooh, I like
P,
that.
see, with the P and the flag. And then we have the area, and honestly, you just plug in your numbers and get your value. That's the deflection. So it's about 0.05 inches of deflection.
I was confused on this one, why we use G and E interchange. I know we're not given an E, but like why we're allowed to swap in G for E.
Yeah, because I've seen the flea equation, but not the flag equation.
Yeah. So the flag equation, G is actually the shear modulus. E is Young's modulus. You use E for like, normal stress and strain kind of situations. But here it was given, what does it say exactly?
It just says G equals, it's a property of the plastic.
It gives us G. So we're dealing with shear stress and strain here. That's why it gives us the shear modulus. So E would be a different number because, as you know, like G and E have an equation that relates them. But in this equation, it just gives us G.
Okay.
So
yeah, that makes sense.
Yeah.
And I've got another question. When we're doing the area, because when I had a different idea for the area on this question, because I saw that we were like working on this surface right here. So I figured that the area would be 3.2 times 4.8, but and that is what you. Sorry, I was thinking this one. I was thinking of a different dimension. How do you decide that dimension?
So you're just asking me, just to clarify your question, you're just asking how to know which dimensions to use because you notice one of them's up here and the other two are down there.
Yeah.
One is a length.
I had that
two are
question
an area.
too.
Yeah. So A is like our cross-sectional area that relates to like that attaches to the plastic block because it's like sliding on the area, and our L is just like the thickness.
That's how shear works.
Yeah, it's like they're like sliding, and then L is just our length, how much of that block.
Okay, cool. Thank you. That clarifies.
Any other questions?
I think that wraps it up. Good stuff.
Thomas, you're next.
I'm Thomas Brandt. I'm going to be doing 5 and 6. So there's no diagram given, so you're gonna have to use your imagination here. But it was a control rod made of yellow brass. Some of the variables were given. One was delta, or squiggly cobra in some academic circles. But the maximum displacement was 0.125 inches. We're given a tension. We're given Young's modulus and a maximum allowable stress of 30. It was 32 KSI, but we multiplied by 1,000 for 32,000 PSI, so it's standard. For this, first we need to solve for strain, which will rearrange Young's modulus equation to solve for that. We can use this in this was an equation given in class. It's strain is equal to the displacement.
The displacement and the length.
The displacement and the length, the delta,
change in
lowercase
length,
delta,
the
change
in
in length,
Yeah.
over our original length. Rearrange this, and we can get. This is actually our answer for B. I don't know. Maybe there's another way you can solve this, but I solved for B first, and then I did A. I found that to be easier. So we get our original length value of. For me, it was 58.59 inches. And then we're going to plug that into the Plee equation, which we talked about in class. So delta is equal to PL over AE. In this case, Chi mentioned this in class too, but our P isn't always going to be given as a P. So all it is a applied force, or a force.
I was going to ask.
So in this case, it was given as tension. So we plug that in for P. We have our length that we just solved for. We have our area, which is going to be, it's a cross-sectional area. So this is a rod, so we can assume it's pi r squared. And then Young's modulus, isolate for r. And then the problem was asking for diameter, so we multiply the radius times 2. And that will give our final answer of 0.1608 inches.
And at the beginning, you were talking about yellow brass or like the property. Would that change theoretically, or what would change given with respect to a different material?
That's a good question, because in a lot of these we're working with aluminum or something like that. And in this case, I think the main thing would be the given. So like a Young's modulus, for example, the stress over strain would be different for different material properties. Allowable, like really all of this
that makes sense.
So the problem will, in this class, they'll probably give you
like the
adjusted values. I doubt. Yeah.
I could see us also, like, I could see her asking something that's rearranged and asking for, like, what would be the allowable or what would be Young's modulus.
Yeah, which all stuff we can calculate.
Yeah.
And also in some questions, they might have different material properties for different parts, so that is something you'll have to account for. But
yeah, because we started to talk about in class how, like, it's a composite parts where it's, like, half one material, half another material, and like it affects it differently. But yeah. All right, thank you, Thomas.
Any other? We good?
Good.
Thomas Brandt.
All right. Hello, I'm Evan. I'm going to be doing 1 and 2. So the first question, number 1, we are looking for the average shearing stress at point B. So we can approach this problem basically just like a statics problem in 30A. So we'll start by doing the moment at B, which the only unknown at that point is E of x. So we'll find that. We'll get 1,333. Then with that, we can do our sum of forces in the Fy and Fx direction, and with that, we'll find By and Bx. And then we will take the magnitude of that and get 2,082.73. And then we'll use our shearing stress equation, which is that force over the area, which will get you 10,000.
So that's just stress is P over A.
Yeah. I probably should have put the equation in, my bad. But then we'll divide that by 1,000 so that we're in KSI, and then you get 10.607. And then for part 2, we are looking for the bearing stress at B. So for that one, we're gonna keep using this magnitude of force at B, and we have an exact equation for bearing stress, so that's pretty simple. That's P over thickness times diameter.
Yeah.
So from there, it's literally just plug and chug, and then just like last time, we'll divide by 1,000 to get into KSI. So 6.66.
To be clear, so for the second part, this P is not the same P as this P. It wasn't.
No. In the general equation, like that is P. You could also use F.
But this is not the same as this value.
No. It's just like they defined it as P in this question.
They just defined the applied force as P, and also it happens to be
in
P in the equation.
Yeah, in the formula.
Which is kind of annoying. Yeah.
Like in the Flea equation, I've always called it the Flea equation because like they use
Yeah. I like the Flea.
Yeah,
better.
I like Flea because like I feel like I'm.
So this is pretty much just a statics problem with like a bit of dynamics.
It's just the very end. You just add a new equation in. Pretty simple.
Yeah.
Could you have taken a moment about something else other than B, you think?
Well, like, it wouldn't be helpful, or at least off the top of my head it wouldn't, because if we took the moment at E, you'd have 2 unknowns, like, well, actually,
no, B would
that
be
would cancel, maybe.
I think it would actually be better.
I might have done B.
I think it would actually objectively be better to do the moment at E. It's a little bit less steps, because By would be in line with the line of action, so there would only be, you'd solve for Bx, and then because you only need the forces at B. We don't need E. So solving for E is a little extraneous.
I think I did moan about E. That's what I was asking. But we were
any method you use to get those numbers.
That we get the same message.
Yeah. All right. Are we good?
Nice.
Yeah.
Thank you.
Thank you. This is number. Wait, can we move back a little bit? Beautiful. This is number 3 and 4. They're pretty much the same thing. One of them's just asking for the necessary diameter for AC and then AD. So the same process. The only difference is going to be right here. So this is the initial force. We're finding the internal forces in AC immediately. And the first thing I was kind of thinking was treating this kind of like Evan's problem and doing like finding a moment and doing the reactions of the whole system and whatnot. But you actually don't need to do all that. All you need to find is the internal forces of AC. So so AC is going to have internal force here, 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 here. But because these two are going to cancel out, all we care about is this right here. So we can set this equal to finding this angle with pretty simple geometry. We can find FAC. And then to be the same thing with FAD, that's just different, longer triangle. That's the only difference in 3 and 4. So once you have your force, We're given that the diameter of a rod of the same material had a maximum stress of 110, and we want to use a safety factor of 3. So that's where this 3 comes in, and this 110. And the rod that they were giving us had a diameter of 20 millimeters. So this becomes a ratio style problem because we're trying to figure out the required diameter over here and comparing it to the same rod of the same material. So using this ratio style problem, we can go ahead and set this up. And initially I was kind of ignoring this 20 millimeters and just trying to solve it like this. But the issue with that you run into is that, number one, you're not using everything that they gave you, and you're going to need to use that. But you're using this 110, which is a property only of the 20 diameter rod. So even though it's the same material, the diameter is going to obviously change that property. So if we were to increase the diameter of this, obviously its maximum stress is going to increase. So if you take this 110 and apply it to here, we don't know that the diameter is going to be 20. So that's why you have to set up as a ratio. So obviously we get some stuff canceling, and then you can just isolate for D. And there you go. You got 34 millimeters.
Clarifying question. What is this question asking? Like, well, you're finding a diameter for it not to break? Is that right?
So not to break under the condition with a safety factor of 3. So that's why we go ahead and divide this maximum stress by 3.
Okay.
Yeah.
Conceptually, are you able to explain like safety factor in like a way that makes sense? Like,
I don't remember the exact equation, but I think it's like the safety factor equals the maximum stress over the applied stress. So like the stress that you actually want to use.
And it's a unitless number that...
Yeah.
The stress over stress.
So it's like, typical safety factor in, it's going to be like 1.5 to 3.
Or that, it depends on the application.
Yeah, of course. So like something that's not moving, you're not going to need as high of a safety factor, but they just wanted a safety factor for this. So just, I guess conceptually what you're asking, it's just like a number that's going to basically just account for extraneous circumstances that you're not able, because not everything is going to be a perfect mathematical equation. I mean, technically it is, but like you can't account for everything when you're building something, so the safety factor gives you that leeway room, and then that's why there's different safety factors for different applications.
But given that it's it's not arbitrary, but like people have different kinds of like ranges they would shoot for.
Yeah.
Or we could safely assume that like the problem would give us the number in like a homework problem or a test where...
Yeah. So something that's like, if you're building a building, it's very easy to have a high safety factor because it's easy to just pour more concrete into your pillar and have more mass and like increase the stability.
And a lot of people are like a lot of people are interacting with the structure. So
exactly. So it's easy to have a high. But something that's like an airplane, you kind of almost need a lower safety factor because you can't just throw on additional parts to make it safer and have a higher stress maximum. You know what I mean?
It's not efficient.
Yeah, exactly. It's not efficient. But that's the conceptual. Yeah. Any other questions?
I think we're good.
All right. I'm Andrew Thompson, by the way. All right.